Okay, I've been doing this series of videos about this important section from Orphanitis, section 1.5.1, where he covers the discrete time Fourier transform and makes various connections to things we've been talking about in this DSP course. Alright, so we are up to the sixth item on the list from section 1.5.1, where he's making the connection between the discrete time Fourier transform and the Z transform. And also this relates to the system frequency response, so I'll talk a little bit more about that as well. Okay, so what we do here in this section is we notice the form of the answer for the DTFT. Alright, and then I'm going to skip down here. This expression is where he defines the Z transform of the signal that we're talking about, and we know how to do that. We put the sample values, we multiply them by Z to the minus n, and then we sum over all n. Okay? So if we let Z equal to e to the j 2 pi ft, okay, and plug that into x hat. Alright, so I'm replacing the Z with e j 2 pi ft. Okay, so this would be sum from n equal minus infinity to infinity, x of nt, and I'm replacing Z, e to the minus j 2 pi ftn. Okay, so I'm using properties of exponentials to get to that. I don't really need these parentheses. Okay, so that's the same thing that we had in the box. Alright, he called this up here in this box, he called this x hat of f. Okay, remember his lowercase f is my uppercase f. Okay, x hat of f. And you know, when I was an undergraduate, this kind of notation I always found to be confusing. Okay, what do you mean by that? It looks intimidating. And really what we're doing here is we were making this overt case that we're going to substitute in for Z e to the j 2 pi ft. But really, you know, it's really just a function of one independent variable. In this case, the independent variable would be f. Okay, it's more common, you know, to write this as the independent variable. So for example, if I normalized frequency and made this in radians per sample, this formula would become sum from n equal minus infinity to infinity of x of n e to the minus j omega n. So I don't explicitly show the e to the j stuff that's in this argument. In fact, if you look, he makes a little notation here where he says at the bottom, if you look in that section, he says abusing the notation. What that means in mathematics is you change the notation a little bit to make things more clear. All right, so he's trying to make it clear that you are substituting in for Z in this particular case. Okay, so we had used that before sort of implicitly, but now it's out there as something that we know. The Z transform is related to the DTFT. All we have to do is look at the values of Z along the unit circle. Okay, so if you had a system with an impulse response h of Z, it's going to have a region of convergence. Okay, when does it make sense to talk about the frequency response of that system? Well, the region of convergence must contain the unit circle. If the unit circle is outside the region of convergence, it doesn't make any sense to plug in those values of Z, and so we would say that the frequency response does not exist. Okay, and we also know that this system would not be BIBO. Okay, so I worked up a really quick example of this. Let's say we had h of n, that's an impulse response, just relabeling what everything is. H of Z, that's the transfer function, which is the Z transform of h of n. I should put out here transfer function. Okay, And if we substitute for z, we get the frequency response of the system. Okay, so if I gave you this particular transform, okay, so here's h of z, and it's defined as this algebraic expression plus this algebraic expression. Can you find h of n? Okay, and so in that case, really that's just an inverse z transform problem. And then we're wondering, so we'll do that in a second, but then we're also wondering, is this system BIBO, and does it have a frequency response? Okay, so I'm showing the region of convergence here, and let me label a few things. This is the 1/2 point, so this radius is 1/2. Here is, this point out here is 3. Okay, so this radius out here is 3. Okay, and so what we know is, because the 1/2, the region of convergence is emanating from the 1/2 term, this particular term is causal. All right, and because the from 1/2 n is not in the region of convergence, okay, that means we are intersecting the disk of radius 3 that comes from the anti-causal term. Okay, so that lets us write down h of n. The 1/2 term is causal, all right, so there's this constant of 4 out front, 4, 1/2 to the n u of n. Okay, and the minus the 6 over 1 minus 3 z to the minus 1 is anti-causal. So remember, the minus sign is already built into that transform. So we'd have a 6 out front, 3 to the minus n, u of minus 1 minus n. All right, so that's the impulse response. Okay, the system is BIBO because if I drew in the unit circle, all right, so I'll try to do that. Here's the unit circle, is supposed to be radius 1. Okay, the unit circle is contained completely inside the region of convergence, therefore the system has a frequency response and it's BIBO. Okay, so we're continuing to put these things together so that you understand some of the basics of DSP, and this concludes our discussion of this important section 1.5.1, the discrete time